my voice, is it coming out?
Yes, it's fine, sir.
Okay, so I thank you very much, all of you, for having me to give this talk. It is a great privilege. I will begin, of course, I'll be talking on multicolor compositions and conjugation of n-color compositions. It is intended to be an expository talk, so nobody is gonna get a headache on this one because it is a challenge that I am contributing to, a kind of puzzle that Ashok Agarwal posed some years ago. I will say a little bit more about the scenario as I go along. I will talk about the background and definitions. I will discuss what I mean by multicolor compositions. Of course, N comes in there at the beginning, which of course reminds one of the N-color compositions. Yes, they are indeed related. Then I'll look at the conjugation of these multicolor compositions, which is actually the main new find here. And then, of course, how this conjugation filters down to that of N-color compositions. This is joint work with Margaret Archibald and Abdulaziz Al-Anazi, and I thank them very much for giving me permission to share this talk with you. And I also want to take this opportunity to thank the organizers of this webinar that is so completely global and exciting and uplifting to all concerned. I am very grateful and privileged. So let me begin with the basic definitions. By a composition, we mean an ordered sequence of integers that sum to n, then they become the composition of n. Of course, n is the weight. They differ from just a set of such objects where the order does not matter, like in partitions here. For example, there are 8 compositions of 4. So as you can see, 3-1 is different from 1-3 and so forth. Okay, but when these are organized in kind of equivalence classes by the order of the parts in decreasing order, they become partitions. There will be exactly 5 equivalence classes. So partitions, the order doesn't matter, but you can specify the order you want to use at a particular time in a particular problem. But my talk today will be based on compositions, where the order matters. It is well known that the number of standard compositions of n is 2 to the power n minus 1, and the generating function is given here, where the number of compositions of 0 is 1 by convention here. So the Ferraz graph of a partition, yes, of course, I will be alluding to partition theory because it has a bigger literature and more venerable history. You see the Ferraz graph, a left justified rows of dots, where each row contains as many dots as the part size. As you can see, this is the Ferraz graph of this partition. And if you want to get the conjugate, now you read the Ferraz graph by columns. Okay, it dates back to Sylvester and so forth, and his students in the past. For example, the conjugate of this partition is clearly this other partition, because you can read by columns. You have 5, you have 4, you have 2, you have 1 and 1. Okay, so it's a reflection about the main diagram, really, if you insist on reading from left to right by rows all the time. So what about a composition. It is similar to the Ferrer's graph of a partition, but this time we shift the dots in a row. We shift the dots in a row so that it begins where the dot in the previous row ends. Okay, so it goes like this. That is why it is called zigzag graph. McMahon, the inventor, called them zigzag graphs because of the shape. And of course, they are treated the same way as Ferrer's graphs, because this is now the zigzag graph representation of this composition. You have 5, you have 3, 1, 2, 2, and the conjugate composition is obtained by reading the zigzag graph by columns. So you have 1, 1, 1, 2, I'm looking at that, and then 1 again, then 3, 2, 1. Okay. There is yet another means of obtaining the conjugates, the algebraic conjugation rule, which somebody can practice and master. If you write a composition in symbolic form like this, where every pair of big parts, I call them big parts, that is parts that are greater than 1 in size, are separated by a string of 1s, abbreviated by exponents. Of course, these exponents can be 0, so that there are no 2 adjacent big parts, so to speak. In this example, for example, this is a 1 beginning. So strictly, this exponent cannot be 0, but others can. The conjugate is now given this way. By looking at it for a couple of minutes, one can begin to understand how it can be done and learn to write it down immediately once you put it in the so-called symbolic form like this. For example, we have this composition. We put it in symbolic form. It looks like this. Then it is set up for conjugation. McMahon said, preparation for conjugation. That's what he said, transition from this form to that form. And you can see how it is obtained according to that rule, after which we pull it down. And if you want to now work with the composition, the resulting conjugate composition, you may decide to leave out the trivial part, which is 1 raised to the power 0, 1 occurring 0 times. Okay, but both of these methods were preceded by a more fundamental method, the so-called line graph, also introduced by McMahon. He says divide a line into n equal segments separated by spaces, then a composition into k parts, which I call k composition of n, corresponds to a choice of k minus 1 from n minus 1 spaces. Of course, this composition has 5 parts, so it needs 4 dots to divide the 5 parts. So this 1 part, 2, 3, 4, 5. And you can see where the dots are. You can see 1, 2, 3, 4. So these unit segments are just like units making up a part. You see? So the conjugate is now obtained by placing dots in the previously unoccupied gaps. Okay, you can even see it as they are aligned. So the dots will now go in there, as you see here. But now there shouldn't be a dot here, okay? So this will represent the conjugate. So we expect that the conjugate will be 1, 1, 1, 1, 2, 1, 3, 2, 1, in agreement with what we obtained earlier using the other 2 methods. Okay. The great pioneers of this study, B.A. McMahon, born in Malta, son of a brigadier general, attended a military academy and later became an artillery officer attaining the rank of major. He pursued top-class mathematics research throughout his military career. McMahon is quite famous. I remember watching the film, the Ramanujan biography film. And you can see what's happened. The man who knew infinity. I think that's the battle of wits between this McMahon and Ramanujan in that movie. And at the end of the day, he had to just accept that he was in the presence of a genius. Even McMahon had to acknowledge Ramanujan's genius. Another great pioneer is Ashok Kumar Agarwal, Punjab University. He is very much around, still promoting mathematics excellence among young and upcoming researchers. They are the pioneers of this study. It's like A.K. Agarwal continued where McMahon stopped, and we are following, trying to contribute, and we are grateful for what they have done. So what are colored compositions? Yeah, generally, when a part come in a given number of types of colors, then we have a colored sequence of parts. So one can come in any colors we prescribe. However, if we limit the colors of a part so that the color attack does not exceed the size of the part, it becomes an n-color composition. N-color composition. Here, an n-color composition is a colored composition in which a part of size m may come in m different colors. So, for example, we have, if you represent it this way, then you see that the parts are the GI and the colors CI. At any point, the color lies strictly between one and the part. How did this all start? For example, there are 8 n-color compositions of 3. Okay, as opposed to the 4 colors of 4 ordinary compositions of 3 we saw earlier. So a little bit of background here. The n-color notion first appeared in a paper of Agarwal Andrews, 1987, where they studied partitions with n copies of n, which essentially you can say is their n-color partitions. Subsequently, Agarwal in 2000 defined n-color composition and explored their properties. He proved that the number of n-color compositions of n is the Fibonacci number, the 2nth Fibonacci number. Of course, the definition is here, and so many other properties. I think it was in this very seminal paper that Agarwal posed a challenge and said, what can be said about the McMahon conjugation method for n-color compositions? Okay, can anybody really make a progress at discovering it? That was when he threw the gauntlet. So many years passed and nobody was able to do anything. Of course, he made his own attempts. We will now see that somebody made some efforts, and of course, this research also contributed to trying to address that challenge. So, multicolor compositions. So if we assign R distinct colors to a part, where R is a number not exceeding the part size, we say that GI is n multicolored. So we are still using the part size as a kind of upper bound for the color sizes. Okay, but now we admit many colors at a time for a part. Okay, So that is, so an n multicolor composition is any composition of n consisting of n multicolored parts. And now, symbolically, of course, one can indicate it as we did before for ordinary n color compositions, but now the colors are sets. They are sets of numbers whereby any element of the color set cannot exceed the part size in, cannot exceed the part size. Okay, so you have a standard composition, you have a corresponding sequence of color sets. For example, we have this as an example of an n multicolor composition. Okay, clearly, if a color of 6 appears here, then it has violated the definition. Okay, so naturally you will see that an n color composition is just an n multicolor composition in which every part has a single thin color set. So it's a natural extension of n color composition. We are going to see another natural extension of n color composition shortly, still under the umbrella of multicolor compositions. How many are these compositions? Well, the enumeration is not particularly difficult. Okay, and I use this to indicate the number of multicolor compositions into k parts. And this is the sum over k. And this is the generating function, which looks quite simple and nice. It's not really difficult to derive it because the color set of a part I is contained in the set of the first I integers. Okay, and we know that the number of subsets of such the first I natural numbers is this. That is non-empty subsets, and that will be the number of colors of the part I that is possible. Of course, we have that. Okay, we have that for a single part, which we now sum over all the parts, or the parts this way, and then in k times, then by routine summation, you obtain that, so that one part is generated by that, and then k of them to give you equal opportunities for all the parts to occur. And then, of course, to obtain the entire thing, we now sum over k. And when you now sum this routine summation, we now give you that result up there. Where, of course, we assume that the number of n multicolor compositions of 0 is 1 by convention. For example, the number of multicolor compositions of 3 is 14. And here they are. Okay, all possible ways of assigning colors to the parts in such a way that the set of colors has a maximal element dominated by the part itself. When you go to the Encyclopedia of Integer Sequences, yes, we did get a hit, and you find that this is the number of generalized compositions where there are 2i minus 1 types of the part I. So you could actually translate it into single color. However, we have seen a lot of that before. And when you have many colors instead, there is a bigger structure per part, so much more to see, and so much more symmetry. Okay. Well, this is a very good mind for enumeration, simple enumeration questions. You can restrict this in several ways. If you want the maximal part occurring to be m at the very most, of course, this is the generating function. all you need to do is to go back here and restrict this to be M here. I cannot exceed M, and simplify. You obtain, and by suitable modifications of that original, you get stronger expressions, such as in which this minimal part is M, and so forth. We can keep on varying it. For example, we may decide that all the color sets are subsets of the first T natural numbers. If we do that, then of course, the first T parts will be kind of arbitrary. Parts higher than T, of course, they are limited to have T, not to have colors of size not exceeding T, and that will give you that. Okay, and if we want every color size to have at most T colors, the construct is a little different. We can go on and on and on, and then there's a lot of things to do here. And of course, for those who want to do more on this in elementary combinatorics, the denominators, if you clear fractions here, for example, you get a recurrence relations that right now nobody knows how to prove combinatorially, you know. So there are so many things open here that the previous single color model cannot provide. So that was the first part. The second part, we want to look at one of the different ways of depicting compositions. Unfortunately, this does not really lead you to any conjugation, but it is quite popular to depict compositions as bar graphs. Okay, a composition like this corresponds to a sequence of columns composed of unit squares, where column J has GJ squares. For example, look at the 4 compositions of 3, how they are represented. Okay, it is quite intuitive what's going on here. This is a single column of 3 squares, and this is 2, 1, 2 here and 1 there. This is 1, 2, and so forth. So what are cracked compositions? A cracked composition is one with potential cracks between the squares in the bar graph representation. Okay? Now, there are 9 cracked compositions of 3. You can see the cracks, I must emphasize, are internal cracks. They are internal cracks. You cannot have cracks at the boundary, but only inside. That means that a part of size 1 cannot be cracked. For example, you see 1, 1, 1 here. There's no crack possible. Okay, but 1, 2, 2 can be cracked only once. So if a part has size R, there are R minus 1 possible position that it can. That means that a part with size at most 1 cannot be cracked. But let us see the connection between cracked compositions, how they provide a very nice, desirable restriction of multicolor compositions. I think Hubert Mansu in their book, this is all they were able to say about cracked compositions. They were not able to relate it to any coloring or any sort. And this is where the novel contribution of this work really begins, because we were able to make this important identification, that a cracked composition is an n multicolor composition in which a part cannot bear the color 1 simultaneously with another color letter. Okay? So here is an example corresponding to these representations. Okay? So once a part has the color 1, it means the part is not cracked at all. But when it has any other bigger color, it is cracked in that position from the bottom up. Like you are climbing from the x-axis, you are going up the y. For example, this is a tray with colors 2 and 3. Is colored level 2 and level 3. This is tray colored in level 3. This is tray colored at level 2. So it's a natural representation. But when you have no color, you have 1 as the color, which means no crack. So this idea that 1 cannot be there together with another color that is bigger than 1 is simply saying that a part cannot be both cracked and uncracked. So that is a natural transition. And with it, we have a lot of flexibility to play with this sort of thing. Okay, however, before even discovering this notation, I will come back to what I just wanted to say, but let us look at enumeration quickly. Of course, it shouldn't be difficult from our experience earlier in enumerating different restricted forms. This is still another class of restrictions where 1 is either the color of the part is either 1 or colored by numbers bigger than 1. See? And then, of course, it gives you quite pleasant kind of enumeration. Yes, the third powers. That is the number of cracked compositions. You can now also think about restrictions, placing restrictions on cracked compositions. For example, if there are exactly m more cracks in the composition, yes, of course, you have this as the enumeration result. Okay. If there are m more cracks per part, okay, of course, if there are m more cracks per part, it means that the part size must be at least m more plus 1 from the definition, of course, and then by reasoning it that way, you obtain, and of course, if there are at most m more cracks per part, you modify that a little bit, you obtain this. This is a very crucial generating function because an n color composition is nothing but cracked compositions with at most 1 crack per part. Okay? That means that we are likely to obtain the generating function of n color compositions if we set m equal to 1 here. Okay, so that's another way to look at n color compositions, which will be very useful shortly. Okay, I must. Hi, Bijan.
Yes, sir.
Yes. An alarm is ringing somewhere in the phone. I need to turn it off.
Yes, sure.
Continue to disturb.
Take your time, yeah.
It's crazy, yeah? All right.
So please unmute it.
Yeah. Okay. So I was just, I was talking about this generating function, but even before discovering all of this, we ran into a kind of identity within the domain of cracked compositions. And you may have already noticed, perhaps if you were observant, the correspondence of these above for generating functions, that the number of cracked compositions of n with exactly m more cracks is equal to the number of cracked compositions of n with m more plus 1 parts. We notice this, And we were able to get a proof. That was ever before we found the notation with respect to multicolor. And that the reason why we were able to give a proof first with using bar graphs. That if you take a bar graph from top down, left to right, anytime you see a crack, you write C. Okay, anytime you see a demarcation between two parts, you write P. Okay, and anytime you go, you cross a crackable position that is not cracked, then you write 0. If you use this as a sequence, it is actually a unique representation of the bar graph representation of a crack composition. So the whole idea is, if you now change the P's, interchange the C's and P's, it will give you the second part. If you notice from here to here, it is just swapping C's and P's from here to here. Okay? Then you will see that indeed that this one has 5 cracks, but those 5 cracks will now become demarcations of parts between cracks. Therefore, they can only demarcate 6 parts if they are separating non-trivial parts. And that gives you the bijection we needed. In terms of the notation of multicolor compositions, which we already explained previously, this is the correspondence, which at first does not, both the bar graph correspondence and this notational representation does not really give one the intuition of anything special happening, okay? Except possibly the sequence representation. Then something happened. Conjugation, eureka, we found it. We found that this is actually a form of conjugation that has been described. And it will not, even though it's not so obvious, of course, superficially you can notice using the algebraic conjugation rule that there's a conjugation going on between these two. If you ignore the colors, you will use the algebraic rule to see that they are really conjugates. However, it becomes more pronounced if we invoke the tiling representation this way. If we now translate those sequences to tilings, which is a kind of modification of the line graph, except now that it has an interior, which suggests a higher dimension, so to speak. So the line has a thickness, unlike the line graph, the tiling. So the process of swapping the C's and P's, you can see, is just changing the cracks with longer lines. I want to call them longer lines or longer bars because they are longer than just the ordinary demarcation between units that make up parts. Okay, you can see that these cracks are replaced by longer lines are replaced by cracks. And with this, you don't even need this sequence representation anymore. We have a conjugation principle that is akin to the line graph of McMahon. However, we are not just claiming it, we are going to put this on a standard platform to show that indeed it does fit into part of possible responses to the challenge of Agawa. For example, we have the full representation of all the n multicolor compositions of 4 in conjugate pairs, which once you understand, master the simple technique of drawing this, which is actually quite simple, you can verify each pair at will. So n color compositions, we are now back to n color compositions. These are crack compositions with at most 1 crack per part. Okay, if we denote n color compositions by L, then of course, as I explained earlier, the generating function for crack compositions with at most m cracks, once m is equal to 1, we give you the well-known familiar generating function for n color compositions, which was found by Agarwal in his seminal paper on the subject. Of course, these are known. The number already mentioned is the 2n Fibonacci number. And of course, this generating function is equivalent to this recurrence relation in a straightforward manner. So the first person that actually responded to the challenge of Agarwal was Brian Hopkins. Brian Hopkins, his theorem says that the number of conjugable n color compositions, or a conjugable n color composition, has this form, okay? And their number is 2 to the power n minus 1 over 2 if n is odd, and 0 if n is even. So that only odd integers can have conjugable n color compositions, according to him. So how does his model work? Okay, according to him, 5 has 4 conjugable n color compositions, okay, which he obtained by means of zigzag graphs. So he modeled his conjugation with zigzag graphs, and you can see the dots, the bullets, dots are colors. So we have 1, 2, 2. Okay, the zigzag graph here, where the color of 1 is 1, this is 2 colored at 2, and 2 colored at 2. When you now read it by columns, you obtain 2 colored at 1, 2 colored at 1, and of course 1 colored at 1. Similarly for 1, 3, 1. When you read it by column, you get 2, 1, 2, according to the colors. Okay, clearly this is bound to be restrictive, as we already saw. That was why, for example, only odd weights, only odd integers can have such a configuration, as he proved. However, by this new model here, if you draw the tiling representation, you find that those colored compositions go to different objects. You know, you can just draw and see they go to different objects. But then many of them are not conjugable by our own model, because you can see here, this is not n color, neither is this, for example. So the two conjugation systems are quite different. However, the present model we are discussing is quite different for a very, very nice reason. One of the nice reasons is that it is substantially more inclusive and does not discriminate between odd or even numbers. So here is the theorem. Conjugable n color composition, the new theorem. The number of CCN, that's what we denote it by, of conjugable n color compositions of n is given by 2 to the power n minus 1. So this does not, whether the whether n is even or odd. And this is substantially bigger, obviously, than just 2 to the power n minus 1 over 2, you know. With this nice, simple result, the generating function is immediate, of course. It's not hard to prove the generating function, and also suitable recurrence relations it may satisfy if one wishes to do that. For example, the number 4 has 15 conjugable n-color compositions. And here they are. Of course, it will always be odd for the simple reason that you have seen 4-colored one repeated. That is the only self-conjugate n-color composition, for a reason we are going to see shortly. All these can be verified quickly by drawing the tiling representation of each partition, which is immediate and intuitive. So the question is, the conjugation method we are discussing here, is it consistent with McMahon's classical tradition? Because that was the question we are trying to address. Of course, we have seen that that of Hopkins, yes, uses the zigzag graph of McMahon. We will see that yes, the answer will be yes, because let us look at the background. In his classic text, McMahon made the following statement. If we think of the number n as a succession of n units arranged in a row, we have n minus 1 spaces between them, which we may fill with a plus sign or leave blank. Okay? The 2 to the power n minus 1 different expressions so obtained are the compositions of n. He was trying to generalize the concept of a composition by saying that, okay, what if we'll use more than 2 different signs to fill the spaces? Then it will give us something else. So this is a depiction of it, where I am using, instead of plus and blank, I'm using 1 and 0. Okay, and then the units I'm using U. So this is what McMahon was describing, which you can translate into standard compositions in a straightforward way. Okay, which of course, you can even go from first column to the third and obtain the corresponding binary representations. It is known that compositions correspond to bit strings. Okay, so you see that the correspondence of the objects in the last 2 columns proves that there is a 1-to-1 correspondence between compositions of n and all binary strings of length n minus 1. Yeah, this can be proved in some other ways. This is not the only way to prove it, as we know. The conjugate C prime of a composition is obtained by swapping zeros and ones in the binary representation and then converting back to a composition. For example, if you have 2, 1, 1, according to the bijection between compositions and B strings, it corresponds to that. If you interchange zeros and ones, you obtain this. Convert this back to a composition, you get that. However, if you use direct conjugation, you will see that the conjugate of 2, 1, 1 is 1, 3. Okay, so that this transition is crucial. So McMahon really intended that model, as one will see if you go through the source of that quotation. You can use more than 2 symbols to fill those n minus 1 spaces. If you do, let's say if you use 3 symbols, then you obtain ternary sequences. Okay? But ternary sequences are enumerated by 3 to the power n minus 1. Ternary sequences of length n minus 1. which is equal to the number of KIIT compositions we already saw. So there is certainly a bijection between the two. There is a one-to-one correspondence between KIIT compositions of n and all ternary sequences of length n minus 1. For example, this is a KIIT composition mapped to its conjugate. You can use the sequence representation we used earlier, or you can convert this to ternary sequences, where I'm using 0, 1, 2, where C is replaced by 2, the P's are replaced by 1, zeros remain what they are. If you now interchange the 1s and 2s, you obtain the ternary sequence representing the KIIT composition. Okay? So you see, naturally, in the case of two symbols, you just swap zeros and ones. In the case of three symbols, all you need to do is to swap ones and twos. So the number of n-color compositions of n is equal to the number of ternary strings in which one occurs between every pair of consecutive twos. This thing needs to be proved, okay? Because that is the answer to the question, how do n-color compositions fit into ternary sequences, okay? We know that general KIIT compositions, we have seen now that they are ternary sequences. But when you add a restriction that one always occurs between every pair of consecutive twos, then they become n-color compositions. And there is a proof, a combinatorial proof here, where it is proved that the number of these ternary sequences satisfy this recurrence, the kind of these ternary sequences with this property. Okay, it's just combinatorial enumeration by conditioning on the last entry of the ternary sequence when it is 0, when it is 2. Of course, when it is 0, it is straightforward. When it is 0 or 1, because once you delete it, you obtain twice n minus 1. But when it is 2 and you delete it, it is not straightforward, okay, because it will now contain some extraneous object here. And the number you can reason out is t to the power n minus 2, okay? And then of course, you obtain that as the case when the last part is 2. So when you combine it, you obtain this recurrence relation. But as you can see, if you compare the recurrence for n-color compositions, you will see that this corresponds to the recurrence relation of the number of n-color compositions of n plus 1. Okay, they match, which shows indeed that this is true. What about conjugable n-color compositions? Where do they fit in? We have been able to narrow down KIIT compositions by bringing in the condition that every pair of adjacent twos must be separated by a 1. What further restriction can we impose to make it conjugable? Every conjugable n-color composition of n may be identified with a ternary sequence of length n minus 1, in which 1 occurs between every pair of consecutive twos, and 2 occurs between every pair of consecutive ones. Okay, and that can be proved. So it's a double something, that you cannot have a consecutive twos in the ternary sequence. You cannot have consecutive ones in the ternary sequence, ignoring the zeros. Okay, and we were able to show that if 1 violates that these are the conditions, C does not contain a pair of adjacent ones for all n greater than 2. C does not contain one between two big parts. Okay, that is now taking it to the composition, the support composition, which you now color, attach colors to. This must be what they satisfy, because if 1 is violated or 2 is violated, you are likely to obtain a pair of adjacent ones, okay, which conjugates to a pair of adjacent 2s in the ternary sequence corresponding to the conjugate. And this entails a part greater than or equal to 3 having at least 2 subscripts, okay? This takes a bit of reflection, and this is quite a condensed form of the proof, but it is so combinatorial, and in practical demonstration, it will become clearer. By the foregoing theorem, let's look at an example. Look at this ternary sequence. It represents the n color composition. 1 colored 1, okay, and then C is colored 3. You can see it, of course, you will see 1, 2, 3, 4, 5, okay, which are the colorable positions, which means that the part must be 6, okay? And then we have a color, the first, and then we have a 2, it's color 3, depending on the, and then if you interchange 1s and 2s here. However, the most important thing to notice is that there are no consecutive, if you ignore the zeros, there are no consecutive 2s and there are no consecutive 1s. So this qualifies as conjugable by the theorem. Okay. If you now interchange 1s and 2s, this becomes the ternary representation of the conjugate. If you now convert this back to a composition, to an n-color composition, you obtain, so that this n-color composition is the conjugate of that. However, the pictorial representation, which is similar to the line graph of McMahon, makes it even clearer. Even without going through ternary sequences, you take this, you represent it like this, 1. You can see 1, 2, 3, 4, 5, 6. Okay, and you see 1, 2, 3. Cracked at this position here, level 2 and 3. All right, that's 6. And then you have 1, 2, 3, cracked at 2, 3, level 3. And you have 1, 2, 3 again, cracked at 2, level 2. And you have 2 without any crack, which means it is colored 1. So the transition to draw this figure is just as easy as drawing line graph for ordinary compositions, okay? And then once you do this, all you need to do is to interchange the longer lines, the line of demarcations between parts, interchange them with cracks, and interchange cracks with those lines, demarcation lines. And this should represent the conjugate, as you can verify after doing that, because this will give you 3, colored 2, you see? And this will give you 1, 2, 3, 4, 5, 6, colored 2, 3, 4, 5, yeah? And this will give you 2, colored 2, and this will give you 4, colored 3. And that gives you an automatic way of, the only issue is that the set of all n color compositions, they are not conjugate closed in the sense that there are some n color compositions whose conjugates are not n color compositions. That is, the conjugates will contain a part that has more than one color at a time. That is the only snag in this whole issue here. Of course, having demonstrated it, one can now prove the main result, which is not really difficult, because you now know that you cannot have 2 consecutive ones or two consecutive twos, and zeros are ignored. Okay, therefore you just have to count alternating sequences of this nature here. Okay, so if J is the number of parts, this one you just choose J positions to place one element, and then the other one will be in the other J position. Therefore, that's why you multiply by 2. Okay, and of course, this one that doesn't contain 1 or 2 at all is just there. Okay, if you do that now and sum over all possible lengths, you see that this, of course, this one represents the unique self-conjugate composition, which is the number n colored 1, because it doesn't have 1 or 2. Once you do it and sum over J, you obtain the result. Okay, of course, you can refine this. Of course, there's a refinement which you can get into K parts, which appears in the main article and so forth and so on. So this is actually what the whole process is about. I hope that you can appreciate the aesthetics of it. Incidentally, this number, as we are going to see in the next, is less than the 2nth Fibonacci number. So that even though it is massively, it's a massive improvement over the model of Brian Hopkins, it still does not encompass all n color compositions. So these are my final thoughts. The number of n color compositions, of course, is the 2nth Fibonacci number. The number, as we just saw, of conjugable n color compositions is this, 2 to the power n minus 1. Then the non-conjugable ones is this. Okay. This is a substantial improvement over Hopkins. This is quite small anyway, and even numbers are not even included. Okay, however, you will see that our number is still substantially smaller than the total number of n color compositions. So many n color compositions are still not conjugable. So this model uses, my model uses the line graph. Previously, the model of Brian Hopkins used Ferrat's graph. So who knows, somebody might come up tomorrow with a model using the algebraic conjugation and maybe get all the n color compositions to be conjugable. This shows that there's no complete answer yet to the question of A.K. Agarwal. So the research continues, but there's no doubt that this has been a reasonable advance on the previous results known. These are some of the references mentioned, and I will rest my case here. Thank you very much.
Thank you, Professor, for your nice presentation. Mr. Utkal, please.
Yes, I am Utkal Prasad Datta, the co-convener for this webinar and assistant professor of mathematics, KIIT deemed to be university. Thank you, Professor Mungi, for a wonderful talk about the multicolor compositions and conjugation of n color compositions. If there are questions from the audience, may I ask?
Good morning, everyone. This is Alain.
Hi.
Yes.
Hi, Alain.
Yes, good morning again. Yes, thank you, Augustine, for your nice talk. In fact, you prove, or it is said that the number of conjugable n color composition, it is the 2 exponent n minus 1.
Yes.
Is it possible? Yes, that is on your slide. No, the next one, yes. The Is it possible that we can find some group of conjugable n colors composition such that the number will be a Fermat number? Because the number you gave 2 exponent n, it is a little -1, it is a little, it has the form of a Fermat number. Is it possible?
Oh, wow.
Fermat's number, it is a number of the form 2 exponent 2n plus 1.
Yes, yes, I know. I'm just thinking about it because the Fermat number itself is just 2 away from this, just 2 larger than 2 to the power n minus 1. Okay. And well, it's not too far away. It seems it's already almost done already, because if you add 2 to this value, you already have a Fermat number. Yes. But I'm not sure a Fermat number can jump out with exactness from this model, from this, because there's wonderful thing about compositions. There's a wonderful symmetry. The symmetry is complete. And even standard compositions, the reason why they are even number in length is that every composition has a unique conjugate. Okay, that's why the formula came out so easily, unlike partitions, where the so-called many self-conjugate partitions make things difficult. So it will not jump out. A Fermat number cannot jump out from this, because there's a perfect symmetrical structure here, and this is what we get. However, as I said earlier, if one can devise a completely new model, because of the 3 McMahon conjugation models, somebody has used the Ferrat's graph, and we saw his results, quite restrictive. And now I have based this on the line graph, and I got a bigger, more inclusive result. Well, the more flexible algebraic conjugation rule, nobody has used it as a model yet. Who knows what might come out of that? I don't know. Perhaps that's where things like what you are thinking about may happen.
Okay, thank you so much for your answer.
All right.
Yeah.
Any further questions from audience?
Sir, your result is about n color composition. So can we study these results for n color partition? Can it possible?
Oh, of course. Actually, n color partitions is there's quite a literature about it, and mostly Agrawal and his students and those supervisors have been working on it. Yes, and they have this symmetric difference which they bring in between 2 parts of an n color partition. But you would expect, obviously, for n color partitions that it will be a little bit more challenging, because the symmetries will not be as smooth and nice as what you see here. But they have done n color partition works, and mostly they have also done n plus t color, where they now allow a part to have more than like a part K to have more than K possible colors, where they say a part K we have K plus T possible colors or types. They have extended it to all of that. And so it is quite a flourishing area of research. And I'm aware I've even referred quite a couple of papers dealing with those extended n color partitions. Because come to think of it, that was actually, as I mentioned earlier, where the very first idea of n color objects originated. because the first paper was written on partitions with n copies of n, which by today's terminology you can call n-color partitions. And it was co-authored by George Andrews and A.K. Agarwal. Okay, and I believe that following subsequent works, perhaps that's why Agarwal now decided to define it for compositions. Unfortunately for him, he found a very nice formula as a Fibonacci number. And then from there, the whole research blossomed.
Thank you, sir.
Is there any more questions?
Yeah,
Okay. If there is no more questions, so let's thank you, Professor Mungi. So, such an informative talk. So I, on the behalf of KIIT deemed to be university and the organizing committee of this webinar, express a hearty thanks to the speaker for spending his valuable time in this busy schedule. I hope that the audience must have benefited from this talk. So thanks again, Professor Mungi, for the same. Thank you, sir.
Thank you very much. I'm grateful.